Hey, sorry, my 2006 computer blew up. So I don't know what happened. I started running some program and no one cared. All right, so I stopped with if we had just any sort of irregularly shaped surface. Sorry. And I picked a point. Well, actually, I should make another surface on the inside. And I said, this is 10 volts, this is 50 volts. And I asked, what was the direction of the electric field at this point? Well, that's actually not so bad to figure out, because we know it has to be perpendicular, and it has to point in a direction from high to low potential. So that would be the E field at that point. Okay. You'll notice that, again, electric fields are going to go from, that I didn't mention that earlier, I don't think, that electric fields go from high to low potential. But if you think about it, that's what a positive charge would do. It would go away from, it would actually go away from the high lines and go toward the low lines. So from high to low potential, as with test charges. So, again, if I was looking at this, I'd look at this point here. If I chose a point over here, the electric field would go like this. Alright, good. So, again, it's going to be perpendicular to this thing, as close as you can get. Okay. So that's how electric fields are going to move. And as we said, the charges themselves are going to move, the test charges are going to move from high to low potential. Negative charges move naturally from low to high potential. And that sort of makes sense. If, let's say we had, say, a set of parallel plates. Positive, negative, and they had some, and you know the electric field's going to be like, is going to go from left to right. And we asked, they said the electric field was, I don't know, 100 newtons per coulomb. And this distance here is 0.01 meters. Well, the total change in the, in this case, E is constant. So, the potential of, from in this case, it's just going to be from A to B, E dot ds. This is a constant, so we're just going to get E A minus B, or ed. So in this case, we're going to have, in this case, the potential is actually going to be bigger over this way as we get closer to the positive plate. So our potential over here, so for this example, it would be 100 times 0.01. Well, that's going to be rough, 1 volt. So if I was drawing equipotentials, they'd have to be parallel to the electric field, so they'd go like this. Very close to plate, it'd be 1 volt. Very close to this plate, it'd be 0 volts. And then I could divide it up accordingly. 0.75, 0.5, that's a little cramped. 0.25 volts. That's volts, and that's volts also. So I can do the same thing there. And you can see they're perpendicular, and I could find the work done to move from one side to the other. Oops. But I actually wanted to use this as an example of what you can do with electric fields. With electric fields, you can actually, and electric potentials, you can actually find out how fast something is going. And we talked a little about this before, that if I want, let's say I put a proton here, and I want to find, and we know that a proton is going to shoot this way, and at this point over here, I want to find out what's its speed. Not its potential. We know that's 0. But what's its speed? Well, to do that, I'd find the potential energy it had over here, which I do by taking Q times V, or I should say change in V as it goes across there. And we're going to have 6 times 10 to the negative 19th. Oh, this is going to be exciting. 1 volt, 1.6 times 10 to the negative 19th joules. And all that energy is going to become kinetic energy. So we're going to set that equal to 1/2 mv squared. So then we can say 1.6 times 10 to the negative 19th joules equals 1/2. That's what, 1.67 times 10 to the negative 27th v squared. When it was some number, and let the calculator tell what it is. So we'll say 1.6 negative times 2 to make up for the 1/2 divided by 0.67. Whoops. 0.67 e to the 27 plus minus equals. Then we'll take the square root of that. I hate the Microsoft calculator. Take inverse squared to get the square root. So in this case, you would get that it was 1.3 times 10 to the 4th meters per second. And it turns out that doesn't matter as long as you know how many equipotential lines you're going to cross. You can find the speed at any point. So if I said, well, what's the speed after it's a quarter away across, I could just say that my delta V was, instead of being 1 volt, 1/4 of a volt, and then I could calculate it the same way. Well, I think I'm out of time, and good luck. If you have any questions, just email me. Thanks.